solar panel array. Yeah, there we go.
Whether you're architecting a new world or reinventing the supply chain, Qualcomm is transforming business to bring intelligent computing everywhere. Helping the auto industry design smarter vehicles.
Date night tonight.
Why don't you find a store that sells simple creamery ice cream?
So you can sit back and enjoy the drive. In progress, creating a smarter, more connected world for everyone.
5G 网络作为重要的新型数字基础设施，是社会信息流动的主动脉，产业转型升级的加速器，也是大国博弈的国之重器。打造自主可控的5G 技术，关乎到国家安全、经济发展与民生福祉。中信科移动隶属于大型高科技央企中国信息通信科技集团，是从事移动通信技术国际标准制定、核心技术研发和产业化的唯一一家央企控股高新技术企业。自成立至今，我们始终坚守打造民族移动通信产业的初心，为我国移动通。
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
So, good afternoon, ladies and gentlemen, my dear friends. It's nice to have you here. Welcome to the 6G meeting. I'm Tao Xiaofeng, a professor from the Beijing University of Post and Telecommunications. And this conference, the 6G Rising Star Young Test Forum, is different because we want to regulate the spirit of handing down and supporting the young scientists. Let's welcome firstly Mr. Zhang Xinsheng, the advisor to the MIT Communication and the Science Tech Commission, to the stage and deliver the open. Dear guests, my not all young scientists, good afternoon. Firstly, please allow me to express my thanks on behalf of the organic committee, especially thanks to the shortlisted young scientists for the 6G Rising Star, and especially to those people and the people from all walks of life who have shown attention and support for development. So actually, ITU 2 years ago issued this ML and actually MM25 really pushed the 6G development, and actually it's really rising tide. And we can describe it in the term that is, it has really started this new landscape of 6G innovation. Every country is working hard to do something with the 6G, especially in topic of AI communication, integrated communication, and sensing, and also as well ubiquitous connection. We promote the 6G technology R&D, and of course, China, as one of the countries, is especially giving extra support, especially support from the government, and now industry, academia, and actually have a lot of explorations and realize a lot of scientific results. Sometimes, actually, after the 6G, meeting, we believe that from society, if we interview people around, we are now still in the early, and we are very much leading the world in 6G. When I look at the science technology in the R&D, we are very excellent so far. And actually, we can see that we have gathered or imported a lot of results. These results have become China's mobile communication, especially 6G communications, a major technology support. So why did I say that? So 6G development or 6G is really a point of vying for attention, and it means we must have a very good scientific innovations, and when it comes to academia, university, actually they have worked together and they have accumulated very good successes, and I believe that these have just laid a very solid foundation for China's 6G development in China. And this actually meeting, this forum, is really intended to award and reward the young scientists star platform. And beginning in this January, we started this call for paper. And when the whole call for paper started in January this year, we got all kinds of very good response. We have even attracted talents from global and global enterprises, and then the young scientists have all received and answered the call for paper. And if you look at the paper we have got, and it's very much in line with the ITU's promotion of 6G, like AI communication and pictures integration and ubiquitous connection. So to make sure that we can review and grade these paper submitted, which is very important, we have organized China's famous experts panel, and after the commenting and also review, we have selected 20 papers with very forward-looking theoretical or scientific. Doesn't say how much papers we have. We have received 54 papers, and we selected 20. And which have possesses really high scientific values and theoretical values. Some papers have very strong, but also very high huge possibility of commercialization. And some young scientists are the future. They also embody the endless possibilities. It is our hope that this 6G platform of Rising Star can really become a platform for exchange between young scientists. It is our hope that we can really lead the future changes. And of course, I hope that young scientists will fulfill our expectations delivering on the 6G topics. And we hope to have your wisdom realized. And for this 20 young scientists, my congratulations goes to end of my speech. Thank you very much, Mr. Zhang from MIT. And Mr. Zhang really view of what young tests have been expected of and also the surprise they give us. Now let's welcome Yiqi Lin, Chair of the Future Forum 5G 6G Working Group, Chief Scientist of China Mobile Research Institute, MIMO Left Fellow. Let's welcome Professor Yi. Thank you. I'm very happy to attend this special meeting. I'd like to say a number. 20 divided by 54. What's the number? 37%. Last December, I went to deliver a keynote speech, and I know that in early times, like IEEE Global Com, the paper accept rate is around 1/3 or even lower than 1/3. And it turns out they have 50% of the paper acceptance rate, and seems like it's really the same level. So actually, we are more rigorous than as a standard. So again, thank you very much. Congratulations on the young scientists who have won this. And you have really have grown a lot from last year. We are really inviting people from the world. So we have people from other countries. Competition is cutthroat. Just like Ms. Zhang has said from IIT, we are all about the collaboration and from between the industry, the university, and academia. So yeah, you can see that you are really doing the researches on the front. You are also the backbone of the researchers. So for every communication infrastructure elevation, there is a lot of sci-tech innovations and even theoretical innovation and even engineering deployment. And a lot of synergy is required to make this innovation happen.
And it's not just about paperwork only. And at the current stage, we're all the way starting from 2018, where we explored the possibility of 6G, all the way up until now, where we're going to roll out. And then from the forefront innovation to industrial innovation to practice and to putting everything into practice, I would say all along the way, we do need your joint efforts as scientists. We can really resolve the interdisciplinary issues, especially when it comes to 6G. Based on our global deployment experiences for 5G, we came to know that in the face of 6G, there are a lot of challenges ahead of opportunities. We need to do computing, we need to do governance, we need to bring everything together. And in this area, we do need to focus on fundamental material science and physics, you name it. And we have to really bring everything together. That's the reason together. Be it for cross-organizational, cross-regional, or cross-industrial or sector collaboration, we need all of them. Hopefully, for all the young scientists in this wave of global, you can really grow all the way from young scientist to global leader eventually. Hoping that the first group of young scientists or founding young scientists, you need to shoulder your due responsibility. And last night, we got our preparational meeting going on for our future work. Hopefully, for next year's fully prepared for that, and hopefully we can make full use of your efforts and do things better. You can take a look at this session. We have chairman from TPC, and we have our vice president, and myself, the chairman of steering committee. You should know that how important this session really is. Since this is so important, and then we believe we do need to really participate more and contribute more to the success of our industry, be it for industrialization or standardization or innovation of 6G, or to put in place or put together this annual event. We can see, and we would like to see your presence. And also, I hope that for this session, we can have very extensive and in-depth exchanges with each other, and this way, I think we can have more ideas going on for breakthrough innovations. Thank you. That's it from me. Thank you, Dr. Yi, for your very speech. By pointing out that for all the young scientists, we indeed need to do a lot more for the setting of 6G standards. And now I would like to give the floor to young scientists, and each one of you will have you can wrap it up by 2 to 3 minutes ahead of the deadline so that you can have a Q&A session. And for each one of you, you could not really use more than 20 minutes because as an MC, we'll really have to control manage the time slots very carefully and rigorously here. And if you do not really end your speech in time, I'll have to stand up and interrupt you. But without further ado, I would like to give the floor to Professor Yin-Wei Liu from the Hong Kong University. First of all, I would like to thank Dr. Yi and Mr. Tao for your speech. I'm so glad to be here in Nanjing. This is my second time. Every time I come here, I'm happy. I've been in London for a full time for the Hong Kong. A crowded place. And secondly, the food here is very good. We only got fish and chips in UK, and in Hong Kong it's okay, but it could not really be comparable with Huayang style cuisines in Nanjing. That's another good point. And today, I would like to bring your attention towards a very new topic, and that's something I've been carefully working on. And before the presentation, I would like to do a small advertisement. Since Dr. Ding Zhibo is here, and he's going to do another keynote on that tomorrow. And if you're interested in that, feel free to watch his presentation. And if you would like just to have something to discuss with him, feel free to do so. And as for my speech today, it's basically about from wireless to near-wide communications. And therefore, I could only cover basically about the basics, and then for case studies, I'm afraid I'll have to skip all of them in the interest of time. And if you're familiar with my talk styles, there are three things: what, why, and how. Why do we need that? And thirdly, how can we possibly realize it? First of all, what is pass? You can take a look at it here. When it comes to pass, we'll have to talk about flexible antenna systems. And it's actually the next step of smart antenna systems. And for me, myself, for star arrays, continuous antenna, I have really done my work on all those areas. Hopefully for antenna, it could be smart. And aperture and electrical magnetic properties, they can all be adjusted. And now let's take a look at it for pass, for pinching. And in Chinese, it's called jiaqu. And it's just like a lamp or pinching tool. And you can see, this is the very thing we talk about. That is the very pinching we have for the waveguide, or sort of antenna. And it can have an outruding part, and we can have like one or two of the pieces there, and in this way we can do the transmitting procedures, and that's actually the prototype of pass in the picture. And now let's move on. Let's take a look at its Docomo's that. And then for example, for this one, this is the 60G transmission device, and that's actually the pinching piece here. And then we can have the radiation of the signals to cover the receivers. But if we remove that, and you can see the title of my speech is from wireless to near-wide communications. What's the best advantage of it? For communications, I would say 50% of the energy comes from loss, even if it's loss plus. And for this pinching piece, it can be deployed here in a near field. Basically, it's about last mile to last meter. What is last mile? Maybe you can take a look at this slide. And that's actually the concept proposed by me. And this solution is basically about the last mile thing. But now we want to make it even more closer. That's the last meter. For example, for waveguide, it's very long and can be easily deployed. And for example, if I work in my office, all I need, and then we can have the pinching piece there. And of course, we can have the very linking of the wireless signal, and then we can intensify that. And right after work, I can release it so that we can avoid wasting it. And basically, that's how we can understand the case. But it's only a concept. the conventional one. If it's blocked, I mean the communication is blocked, and then of course the signal might be weakened. Then what we do here, and even if that is the case, we can really move the very pinching piece all the way from here, and that's actually the communication I have here. If you can stand higher, then you can see things further, and that's actually the case I'm talking about, and that's the concept we look to propose. It's from wireless to near wired communication for pass. And as for this paper, I worked together with Mr. Ding, and we worked together to do the design for about it. Then why we do need to do that? There are three things. First of all, it's about large-scale antenna configuration. When we're working on star kappa arrays in the first place, even if it's flexible, and you can really change the phase or amplitude of that, if it's blocked, then I cannot really do things further away. We'll really have to start all over there again if that's the case, but now we can just move, I would say, the antenna or the pinching piece all the way from here to further places, maybe across meters or dozens of meters away. And secondly, it's about the scalable implementation. I used to work on star by myself, and we have continuous antenna kappa. As long as it's being done, if you want to really add or delete one wire or antenna, it's really going to be difficult. But it's another story when it comes to the pass. You can forever do adjustments of that. You can simply bring the pinching piece together with, put it there or remove it as you see fit. And thirdly, it's about near field advantages. Of course, we can do a lot of contributions in this regard. Of course, it's always being near field thing. Why is that? Because it's basically about the distance between the very position of the pinching piece to the location where you are. But of course, we have the near focusing as well as other, I would say, advantages. Of course, we can have issues like aperture loss. For example, if you want to go to watch movie, of course you cannot really see the entire of the screen if you sit in row number 1, and that's actually the near field disadvantage, but it has its pros and cons, and that's actually the reason why I bring this very case to your attention. Then what is my contribution? And since you work on this very passing or pass system, then what is my contribution? And it's basically about modeling. And you can take a look at this case. First of all, it's about physics principle. What is the difference between the conventional and new dielectric waveguide? That's actually how it looks like. In the past, it's been covered by metal. But now, we hope that it can be leaked in this way for the waveguide. And if it's really exposed in the air, that's what I'm talking about. For example, we have 28, 60, and 150 gigahertz. And you can see that's the related part of, that's the case I would like to talk about. And let's move on. At the electromagnetic coupling here, and that's what I'm good at. It's modeling. For example, you can see those two waveguides, and we got coupling in between. And in the first place, we did not really like it. But now we want to do something new. That signal, that's what we want. In the first place, it's about wired communication, but now we want to make it wireless, and that's the reason why we have the coupling as well as the pinching piece here. And then why and how do we do the coupling? Here you can see this is the wireless communication signal, and we have this very pinching piece there, and then we have kappa. That's actually the lens, and it has to do with two things. For example, we got this width of the kappa, and then it has something to do with the very distance, and that's actually the two factors that play here. Or in other words, with these two couples, it can be done. Then be it for a clamp or pitching or other piece, it's okay. All we need to do is just to have a good management control over the distance. And then why we still need this pass or pinching piece? Or it has two or double meanings here. It needs to be transmitted to you. Another example, if we play basketball, you can just throw the ball in the air or along the ground, but the best hands to personally deliver the basketball or the ball itself to you. That's actually the safest way to do it. And let's forget about the maths here. Of course, we'll have to first of all, but these are actually the mathematical details. We'll have to skip it. And those are the two things I've just talked about. The first one is about the coupled length, and you can see the two curves. It's pinching antenna power with the blue line, and the dashed red line is waveguide power. When it comes to 0, we do not really have coupled lengths and signals. It's actually in the waveguide. And when it's 7 millimeters, then we see the exposures of the antenna, and in this case, waveguide power has no signal anymore. And now, what about the spacing's correlation with this very normalized power? When it comes to 0.7 millimeters, you can see that for the antenna, its power is here, and if it's waveguide, the power, you can see if 7 millimeters, it's almost diminishing to 0, and it's all there in the pitching part, and that's what actually I'm talking about. Signal modeling, and it's actually interdisciplinary collaboration for material antenna professionals, and they do their work, and for us, the work we do and we used to do in the past. First of all, we have the waveguide propagation and plus free space propagation, and this is actually the wired and wireless part being combined together. And also we have two models: equal power model, the other one proportional waver model.
Suppose there are 4 pinches and each get 1 force, but actually when you do it, and 4 pinches, if they're the same thing, they have the same sequences, and so that is the model that I can use for the power model. Then let's continue. And next is how, and actually it's really the results of brainstorming, but not readily available. It's really interesting as the idea goes. First is the user-centric activation. What does it mean? So then I have this pinch when I go to work, and I sit on my position and in my seat, and this is waveguide. Signal is bad. It's just like charging my cell phone. I had this there, and the signal leaks from this side, right? And so I feel bad, and I want to position of seating. I sat here, and I put my pinch there in different place, and the signal got out from this side. So it's like it's everywhere wherever you go, and of course it has many other issues. You may argue this is bad, and that may just issue of exposure, and nothing is good or purely bad. And second is base station or BS centric activation. BS is so for instance for an operator, we need to do something. And for instance, activation method are any of the 3. Yeah. For instance, I give you one thing which is easier to realize, which is this is like piano keyboards. And what do we mean by that? I try to use this pinch in the position and click these 2 pinches in that position. So it's like I'm playing with the piano keyboard. I'm talking about outdoorsy and a little bit moving from places, just like high-speed way. And also spec-to-X communication and UAV. You need a very fast switching, and in real cases, and it may develop be a pinch and maybe something else. And now we all have 0, 1. Actually, in the future, we can 0 to 1, and we can have continuous adjustment. And so they have very huge range of liberty, and we are excited about this because it's very same as what we thought. And when we do normal, it's the same thing. It's the same as a normal. And we give you a lot of liberty and imagination spaces. That's just beautiful. And next is, we have new thinking. I've been talking to my dad about it, and he will say that 0 line, we can have this electrical current. I'm on the outside. I just something I heard, and we have a lot of spaces. And actually look at it now. the communication in are also using I'm talking about underground cables, and this idea is the same, which is getting lines from underground. More or less, I share these similar concepts. My concept is to make it more simple. We also have something else, which is continuous activation, right? And it's like this, devices in the hotel rooms, and this activation is good because it is electronically controlled. It's more easily. It's mechanical. It has good. It can save a lot of pinches. And for me, I do academia. I only talk about pros and cons. So how engineering and industrial application, not my story. And we also have semi-continuous. The best thing about it is we have complete. I activate it in the site, and I give it as a limited range of motion. From Richard's perspective, you may think just like a star. It's different from star. Let me just give you some stories. In past, star maybe base station to stars. Now I feel that base station and star have the waveguide as a connector, and these two are coupled together and near field. And the star can you using the far field, and also why do we say it has a? It's really normal, and that is normal, and it's like every waveguide has to transmit different signals, and if we can normal, that is the case, and also if I put everything one place, if I can change it into multiplexing architecture, that is MoMA. So different waves guides different waves. I have given name, which is we have pinching beamforming, then we have transmit. If I do this case, transmit forming is very much like well past, and pinch beamforming is like passive, but they are different. And one is near field, the second is far field. So every time I move, the star is just a phase that I change. If I the together with this phase. Then we also have application scenario. What can you do with it in the future? Economy, which is very crazy, and if you do the inside, if I use it's hard for us to serve the inside from the outside. I put it in, then I put a pinch overhead, and we also have other things like Swift and Norma. And Norma is a natural. It's really a good case for Norma because one with our case, and we also have a security. For instance, this is but now I can circumvent the whole thing. ISAC is easy to use. I know I talk about in near field sensing, so naturally it must have a near field sensing. So near field sensing is beautiful as a technology because it can sense trucks, and also the good thing is that I can really follow the drones whereabouts. Track tracing, people really rely on these cameras and sensors, but now we have wireless signals are really strong. It's just that we never used. The past can help us to better realize these devices. So if the antenna is so big, people don't believe it. How to do it? Okay. And in this case, we can use discrete, which is like playing the piano keyboard. And we have another scenario, like it's a curtain. This is it. I have 1 minute. You can have time for questions. So if you have anything, we have a lot of directions, and for you to use it, you can always send me the emails. So these papers are available for downloading on archive, and also so one slide back. Sorry. Anyway, If you have a question, you can ask question. I want to control my time. Thank you. Someone please pass the mic around. Yes, make sure he or she use a mic. Hello, I have a question. In my understanding, it's for one. It's for single frequency. What if I change the frequency? Can it? It's a good question. This is my understanding. But for instance, I'm talking about the multi-frequency and using, and yeah, it's relevant to the width and also frequency. Future, the direction we can take. I see you talk about this custom theory. If you deviate from the critical couple condition, the leaky wave amplitude may change. Yes, very flexible. In future, power and pinch numbers and even circles relay. These are all possible scenarios, but I just put out this question. So please take a seat. Thank you. Very good control of time. Now let's invite the second speaker, Sun Qi. Yeah. Dear expert, good afternoon. I am Sun Qi from China Mobile. Mr. Liu is really full of passion and interesting. Hope that my talk will not give you too much boredom. And because AI and communication are really the future and the mainstay for not just for 6th Gen or 6G, but for many future G. I talk about these two things, communication and AI in 6G. Mainly from industrial perspective, I pay attention to the AI infrastructure. How we transition from how we can industrialize it and standardize it. Two things about the operator's perspective, industrial perspective on the combination of the two. ITU has defined that AI and communication are one of the future 6 for our perspective. AI technology. AI is also the application of commercialization. We all say, okay, AI for run. How can I leverage the AI, make sure it can be combined with traditional ICT technologies to improve the efficiency and also automated realization. So for level 1 to level 3, we have a lot of changes in OEM. And secondly, AI is not just a technology for communication. AI is for every industry. AI is like an industry or business. And so our 6G network has infrastructure instead of 6G being just a wireless infrastructure. So we need to think about how we can realize the future where internet or network is the and infrastructure of communication. So from this perspective, AI for Run is really about using the new technologies to realize the sea change in the technology paradigm, and it uses the data driver to realize automation and optimization of internet. And how do we increase new computing power? And how can we have more data? And how can we have better communication based? And how do we realize a model to improve its efficiency and also its performances limit? I said that AI is a business. It's more like an infrastructure, and AI can help us to realize a paradigm shift in services. And in future, operator it will provide not just ubiquitous service, but also ubiquitous AI tech computing. So what can we provide? First is traditional and trustworthy communication connection. Secondly, is ubiquitous low latency computing and also data sensing and other open technology. We will change it from the connection network to X as a service. And from the technology perspective, what do they mean to our internet? And these are two very different perspectives. First, AI for Run. Let's take a look at it. And from the model perspective, AI for Run can serve the RRC, MAC, and PHY. And we need to consider with the internet, can we support the full lifecycle management of AI model so that we can run it very reliably? Secondly, from the AI for run perspective, data is generated, collected, and processed by RAN. Thirdly, from computers, so we use ASICs and it's a low power consumption, very good real timeness, and computing may bring about new demands for computing, and it's different. And for GPU, given a lot of attention, we also have AI RAN associations exploring the possibility of pure GPU, but it is a challenging solution. And so let's take a look at the RAN for AI. It's for application, and we want to do the AI model lifecycle management from data perspective. Traditionally, data was coming through a pipeline. I don't sense what is in the data. I don't know what. The third thing is that from a computing perspective, now the AI models, big or small, rely on the centralized and edge cloud devices and infrastructure. And as a cloud, we can provide a very good edge computing close to the consumer. And that is also feature opportunities of low latency. And we found that they have very good impacts. We need to continue a discussion. 6G is a systematic structure and not a single dot technology. We need to think about how we can do it and turn them into a highly operable and system. Make sure it is. We need to consider the efficacy and also the efficiency. Let's take it a little further, and that is AI for RAN has been for almost 1 decade.
And based on the AI feature extraction as well as the analytical solution, we can do all of them, covering layer 3 coverage optimization and mobility optimization, load balancing, slicing optimization, energy saving. We can make sure that we got the 10-second deployment and also millisecond signal processing. It can be widely and universally applied. And in the first place, we didn't really consider AI as a factor. It's only add along. And then right afterwards, we started to think about how can we improve data collection and to better introducing the application of AI. And then we got AI interface. It's becoming a very new topic here, and it's gonna be a very important starting point for 6G standard setting. And for us, we try to understand AI as in how to really resolve the robustness as the ubiquity issue. Hopefully, we're going to see a lot more AI-driven devices being used. And also, it's not just about signal processing. As a matter of fact, I would say it's already being used. I would say at commercial level for China Mobile, we have all kinds of like multiple networks, synergistic collaboration platform. It has already been used on the ground for different base stations, which can help us to drive down the energy consumption. And then for run AI, we want to enable access for pervasive mobile AI apps, and we believe enabling AI, it's more about, and it's actually about RAN, and we want to really have the very ubiquitous low latency AI services to users. And in the first place, we really want to do computing offloading while at the same time data exposure, and also we need to have tokens, models, and multimodal data. It's actually and in the future, I would say for engineering part in standard setting, we need to think about how can we better demonstrate support. We have already mentioned a lot of demands things. It's actually about its status quo for applications of the network adjustments. And now we can take one step further to talk about some technical details. First of all, it's actually about system design. How should we do that? We want to focus on unified architecture making to support both AI for RAN and RAN for AI. And one more thing, From the perspective of operator, we want to think about the future investment. That is based on effective investment in infrastructure. How can we really improve and maximize the return on investment? And maybe in the future, we need to have protocols for sensing, computing, and how to combine that better with AI. That's something we need to think about systematically. And be it for AI for run or run for AI, there are a lot of technical issues like standards part or protocol part. We want to make sure the overall system can of AI for run, we need to have reliable AI ML models and lifetime management. Of course, for different models, they have different distribution of data and different features. For communication system, it needs to be highly reliable. It should break down easily, but we do need to take time to explore how we can do that better and how to make sure at the same time it's really usable on the ground. That's actually secondly for AI use, I would say we need to make sure that the efficient data collection is there at a low cost. And thirdly, since we got these pervasive and ubiquitous base stations, we need to think about how can we possibly enable distributed AI and machine learning or transfer learning or AI agent or agentic AI, including some of the agentic AI protocols compatibility. That's something we need to all think about. And for RAN for AI, we need to think about the AI ML services. Of course, we also need to the synergy between communication as well as computing. That's actually the right and important direction for us to follow. And right after that, maybe from the perspective of China Mobile, we can share some of our ideas with you. First of all, it's about RAN's architecture. How can we change and fine-tune that? With the introduction of AI for our data, our computing, I would say at different levels, they have already been applied. Since data is distributed at different levels, and we need to have the real-time requirements like second, millisecond, or even shorter period of second latency, I would say that data as well as computing functions should be deployed based on the actual demand. And secondly, we need to think about how can we optimize computing consumption, and in this way we need to achieve the synergy between computing power and computing itself. With that, we need to have this centralized AI intelligence to make sure the synergy is there, to make sure that the learning inference can all be improved. And with all those things, for all those servicization functionality is there, and we can further open up our internet to make sure that AI service could be better used. And in the information architecture, we have already done part of the experiments here for verification of the prototype. And some of them have already been widely applied. This is another that is basically AI-empowered QoS or QoE insurance. And outside of our base stations, we have the very centralized computing unit. And we want to think about how can we possibly identify different businesses, like in congestion scenario, the experience might not be that good, and then with AI in place, we could do application classification. And on top of that, on the interference as well as the speed of the internet, we can effectively predict the user experiences. Then what's the value of it? In the PRG's coverage is very low, and in some scenarios, some of the user experiences, it's not that good. For example, for big concert, for some of the subscription users, they might need very better services, but actually they could not really possibly have that at the moment. And based on the package of service, we want to roll out even more differentiated packages. And with our solution, we can make it happen. And from the prototype here, with AI empowering solution for congestion scenario, for the speed for the high-level subscription users, the experiences have already been improved. And technique, I would say it's already being used for 5,000 base stations, and I feel like in this year, its application might be further scaled up. And second case, it's basically for RAM for AI, and then On top of that, how could we possibly have the edge computing AI service? And now I experiences with you by working together with our counterparts from Beijing University of Post Communications, and we have here. At the same time, the software of the base stations have been deployed, so it's with our Edge AI, and we use YOLO AI data inspection. For example, if the user's traffic is very high, and then under this circumstance, for the computing resources for monitoring, it's not enough. And then by optimizing both the communication as well as the computing, we can do the scale up of the capacity to make sure the upload and download ability will not be sabotaged, while at the same time for AI's computing power, they can do migration across different nodes, and then for user communication be improved at the same time. And now let's take a look at standardization. For release 16 and onwards, for 3G, the 5G to the wireless access, we think about how we can really improve performance all along the way. For 6G standardization, it's really urgent. In March, we have the workshop on RAN, and in upcoming June, we're going to have the entire study for wireless access, and in 2029 or in June 2029, we're going to the 3GPP 6G standards. It's very important. With the first version in the first place, could we possibly really do the industrialization and commercialization of it? And that's actually a huge challenge for the entire industry, as in what we need to do in the first version. What should be standardized at first? With all those uncertainties, we know AI at the same time is developing very fast. Then how can we ensure we can fulfill the very demands in our businesses while at the same time it should be really flexible and adaptive at the same time? That's something we need to think about very carefully. And in this area, for standardization compared with academic research, what is the difference between them? I feel like in the entire process of research, we focus a little bit more on models, whether the performance of that is good. With 1 or 2% of the optimization, that's actually okay. However, for standardization, they need to think about things from systematic design like interoperability as well as connectivity between different systems. And therefore, for standardization, we need to think about the realization of the models themselves. For the end users, we're going to rely on your industrial innovations. However, its structure can be standardized. And also, we can think about standardization in use cases, be it for AI for run or run for AI, what's their requirements, and how could they possibly guide our design of the system better. And then it's about framework, architecture, and functionalities of AI ML, like model management as well as lifecycle management, and also how to really roll out AI-based new services and to do the interoperability test. Since the time is limited, I have to really present everything very fast. First of all, it's about 5G use cases. We explored a lot in this area. And in communication area, we are trying to proactively embrace AI. There are a lot of lessons and experiences that can be borrowed for 6G deployment, and also for 6G for 3GPP SA1, we consider that, and also for run for AIF for run, we need to think about what are the emerging scenarios for both of them to make sure the communication or mobile communication system can be really adaptive to the future needs. And then for a vision and framework, we have different work groups like run 1, run 4, and it's basically no unified design. It's more of a bottom-up thing. And after this experience, we need to think about how to have the unified framework to be applied for different work groups. We have different, we want to have the same as well as the language to communicate with each other. And also there are new and emerging AI technologies. How could we possibly adapt to those and do design accordingly? That matters as well. And then it's about architecture or low-cost data collection as well as effective data transmission and model management for different scenarios like this. Our own takeaways, but in the interest of time, I have to stop here. If you are interested in my presentation, feel free to contact me. Thank you so much. Thank you for your presentation. Is there any question coming from the floor, please? AI for run and run for AI, what are their respective applications? And that's actually the question I would like to throw to ourselves. It's really hard for me to answer at the time. For AI for run, the essence of that it's about improving the performance of the network. And then from the perspective of maintenance and operation, there has been a lot of gains. For example, it's being widely applied. And then in the next step, we need to think about how much gains we possibly have. And in our industry, we have done a lot of, I would say, extensive tests in some of the extreme scenarios like scenarios with high mobility as well as interference. Sometimes we can have 50% of the improvement, and it's really attractive because with limited resources, we can achieve even more. For operators, basically through technological or technical innovations, we can have more traffic. That's something we would like to see, but more importantly, we need to balance this with the cost. With AI infrastructure, can be more and greater energy consumption, but we are still in the exploration process. We need to take more time to dive into that. For run for AI, be it for communication, embracing AI, or providing services to AI, it's gonna be developing. For mobilized AI, that's gonna be a huge opportunity for us. We want to focus on video, but it's not there. And right afterwards, we all of a sudden have WeChat. For mobilized or mobile businesses, hopefully we can demonstrate our support to represents a huge opportunity in addition to challenges, and we have different technological routes, and we feel like to AI agents, they are all interactive, generative AI, and that's really very important, I would say, requirements for low latency.
And also embodied AI. We are also paying attention to this embodied AI. Thank you very much for the answer. Next, let's welcome Mr. Zhang Jiao, who is director of the Pervasive Communication Research Center of Purple Mountain Laboratories. Thank you very much, Mr. Tao, for the introduction. Jiao from Purple Mountain Laboratory, and we're happy to have the chance to talk to you about our last 2 or 3 years work. My topic is terabyte photonic terahertz real-time communication architecture, key technology, and verification. This is my outline. First, motivation, background. Second is key technologies. Third is the description of demonstration, the experimental setup and results, and also I concluded with conclusion. This has been seen a lot times, and Mr. Zhang has said that we have this. It's really it has 6 aspects for 6G, and start with 5G, and we go. Look at the huge capacity. I try to extend the possibility of our capacity, and we have immersive communication, and yes, it's there, and the peak speed rate as a consensus is 1 terabyte, and so it's 100 times increase compared to 5G. Okay, if we can realize this speed, we need new breakthroughs in the system, and terahertz has the special bandwidth. It can support 100 gigabytes and even several terabytes. And so we choose higher frequency band to realize the transmission at high speed, and RAC 19 and RTO's WRC 19, and so actually we have a lot of standardization and record 19 and from these band frequencies, we provide we have this bandwidth for mobile communication and even transition communication. In May last year, ITUR has approved a new report about the technical stability of LMT in bands above 100 gigahertz. So what are the challenges of terahertz communication? 3 technical points. Firstly, how to transfer fast, and especially in over 100 gigahertz, and so actually production is a challenge. And when it comes to the wideband, it's a challenge. Secondly, how do we travel far? So terahertz, when it goes above 100 bps, the loss can be very big in propagation. And if we do this long distance coverage, it's a big challenge. And so how do we tackle this issue? Last question is the signal processing. If the signal is above 100 gigabytes, it's hard to realize real-time processing. If you develop with FTC, it's very cost-effective. It's very costly. So how can we do this from a low-budget perspective? And our work mainly focus on the three top key. Right, for developing technology. First is generation of, and the second is make sure it can cover larger areas. Thirdly is signal processing, and as we know, about this fiber optic network and the core, and also we have all kinds of internets. Last mile, it's all covered by fiber optics, and the concept is that we must have the total fiber optic coverage, and that is fiber optic plus terahertz waves must have all this kind of integration. That is, when fiber optic was inconvenient, we can have the terahertz transmission system installation. And yeah, we must have seamless connection between fiber and terahertz. When it comes to indoor short range coverage, it must also do the work. So in the optical module is very complete and mature. When it is 10G or 100G, it's the same thing. And when it comes to the relevant, so we have even 1 terabyte. And so we can replicate our existing optical network technology to empower the possibility of terahertz. First is signal production. That is, we can still use our available components per. Secondly, the fiber optics have a wide coverage because it's really the last mileage. And so Mr. Liu talked about the near wired, because near wired have a wider range, and it has two advantages. First is mobility and convenience, and second is a wider ranging coverage of the fiber optics. And there are two questions to rule out. Second, firstly, how do we signal, and that is terahertz to signal generation. How do we make happen? The main technologies are two. Yes, first is from electronic perspective. It has this transmission. And so if we use the harmonics, and also the intervention may be very strong, and even the phase relevant noise may even increase. So if the signal is ultra bandwidth, the bottleneck will be hit very early, and because the harmonics intervention, it's hard. The second method is electrical plus optical. So two light waves can really go through a teledyne to realize that this production of I can use so this is the two major methods, and we actually have compared technologies. And so first, look, we compare the speed, because the first optical, we can use this ultra bandwidth methodology. It's easy to realize over 100 Gbps transmission, and the signal quality is very good. And secondly, because we use laser devices, so we can modulate frequency very flexibly. If I need 100 gigabyte G, we can realize continuous adjustment of the wavelengths. And now we have this seamless connection. And so, but for light, it has issues, and it has some strengths in power. And when it comes to long range, electricity has a wider coverage than optical solutions, and we have taken to make sure our photons can be covering a wider range of areas. Now, so we talk about the terahertz production from the reception side. We change from the terahertz to optical. The main technology are baseband to optical, and so first is the baseband to optical, BB to optical. In this way, we can realize the transition from the hertz to optical. Then we have the direction modulated to optical domain. The third is the intermediate frequency. Then IF is changed to optical. So we analyze the strengths and weaknesses. Firstly, you change it to base. You start with BB, and it has a very high requirement for the terahertz accumulation. That especially when it comes to RQ and balances. Secondly, the drivers and the latency must also be adjusted. The second methodology is the direct modulation, and so if it goes about 300 G, and the requirement is really high, mainly limited to labs. Commercialization is challenging. And so the IF to optical, we use a very methodology, and really we focus on the third method, which is commercially available and mature components to do the work. So this is a case point, and coming from the Germany institute. So it also use this MIMO real-time optical modem, and I'm talking about 100 B. 33 for for the reception and transmission, and we have the amplifier. And this method is the first case of its kind. The pure electrical method is limited because the bandwidth is 25 gigahertz. The distance is very low, just 50 centimeters. It has a valid data. It's the first, and terahertz can be combined with optical network. We don't need a and so this is another solution that is for receiving and transmitting, and these are part of the phase period, and we have this production of terahertz. That for receiving end, we have a mixed method going back to light, and of course we have this have a normal methodology, and of course we have this we have a coupling method to realize transition. This is of summary, and beginning 2020, we all the way to 2021, we had the first break. That is, we have real-time 100G at 360 gigahertz. In 2022, we has this double lambda wavelength 200G fiber terahertz fiber seamless integration system, and 2024, and in May 2023. Wavelengths solution. Last May, we have real-time net 1 per second with simultaneous multi. And of course, these works are published in our top journals and also high-impact conferences. Now let's take a look at some demonstration. Is the 1 terabyte case, 1 terabyte per second case. Have 4 parts. It has the fiber optic network, which can support over 1 terabyte on receiving transmitting end. We have optical to terahertz by oscillation, which is 2 by 2 MIMO wireless. We have five channels, 100 and 107. For each, we have 170 to 260, and we also cover certain which is 260 to 400, and we have 200 gigabytes, and we have 5 channels which can realize 1 terabyte. And the picture you can see on the lower right is the actual site picture. For every journal, we have 2 by 2 MIMO because terahertz wave short lambda, and due to the speed limit, we have the 3 meters of distance for validation purposes. And now let's look at the receiving end. That is a terahertz to optical converter, and we have 2 methods. The first is the 200 gigabytes for single wavelength, single lambda, and we have double wavelength, double or dual lambda, which is 400.
最后呢，我们对
So for 10 to 500 GHz, we can have the full coverage and we can do the work for every frequency range. And the speed is 100. So the total byte per second. And eventually, we have built up this whole system where we have a streaming platform there. We want to see the capacity to release to do the streaming of the videos, and we have 2 wavelengths altogether. And we set up this platform and actually evaluate the transmission and transduction of signals. And with this network mesh system, we happening, and we know terahertz transmission is really strong. And actually, we conduct this validation test with different materials. So please play the video.
首先呢，
First of all, it's about paper. And obviously, it can go through that very easily without too much influence on that. And then it's plastic. It has 2 millimeters thickness, and it can go through that, no problem with it. And finally, it's about metal. But when it comes to its own transmission. At the same time, for our lab, we have put in place the 400 GB streaming service platform, and maybe you have already visited that by yourself. And 280 and 340 gigahertz respectively, we measure the very streaming media there, and we have these very 3x3 4K displays, clusters, or array. And for the relevant modules, it can really be transmitted to the receiver side, and then we're going to display and show the ability of that. Of course, is within a short period of time, but at the same time, we're going to also do the very regular demo. It's no problem at all, and it's basically about indoor transmission. If we want to really cover even larger areas or spaces, we need to really cover longer. And in this area, outdoor, we have put in place an outdoor verification system. And it's actually in the space between our 2 buildings and our lab. It's about 200 meters wireless link. Still, we can just play our real-time streaming. And of course, we have this very 20 by 20 MIMO. And of course, we can improve the very coupling to really enable the very longer distance transmission. And as for this function, that's something we've finished and accomplished recently. It's about outdoor 2.2 kilometers wireless with 32 GBPs at 335 gigahertz. And it's actually a photonic assistant continuous wave traveling wave tube amplifier, and obviously the power there or output power there is very high with 3 watt and with 500 dB gain, and in this way we can really make up or fill in the gap here. In this way we can effectively really lengthen the distance here. And finally, it's about the prospective scenarios as well as the very open issue conclusions. And for prospective scenarios, we can really replace the optical fiber solution, and we can really have the point-to-point link. And for emergency scenarios with earthquakes or, for example, natural disasters like flooding, we can really do and enable the 6G emergency communication as well. And also indoor speaking, we can really use that to really replace all tremendous optical fibers, and really be compatible with this 4K video display. And finally, it's about discussion of the open questions. And the work we've already done has been demonstrated by the pictures. The first of all, it's actually a photonic. Secondly, it's about high gain and large bandwidth terahertz amplification techniques. We've just talked about point-to-point communication, but if it's mobile, of course, we'll have to rely on the photon technique, and that's something we have already done. And one more thing, we have already talked about discrete electronic devices. Then how could we really do the integrated photonics for terahertz radio access? The very atmospheric loss is huge for terahertz communication, and that's the reason why we work on terahertz FSO ultra reliable communication solution. And in this way, for complex channels, rain, fog, and turbulence, they can be really complementary to each other, and that's the reason why we would like to dive into that recently. That's it for my speech, and I would like to really thank the entire team for supporting and helping me finish this very project. And feel free also to pay attention to our scientific work, and thank you, and look forward to our collaboration with each other. Thank you. Any questions? And just now, we are thinking about the scenarios that under which it can be applied. You talk about fiber replacement and internet. And I would say for 6G standards or 6G itself, it's not directly linked to them. But anyway, I feel like it's really impressive. In your work, there are a lot of, I would say, profound and advanced technologies. And in your project or issue, and compared with our counterparts overseas, or globally speaking, what's the very current status quo of your work? Thank you for your comments, really. By fellow academician Wu, it's basically niche using scenarios. I'm afraid that for 100 gigabytes or 1T scenarios, they have not yet been there. And for our comparison with our been leading the way in speed, 401T speed, and for 1T speed, we have already made a report presentation in Germany. Therefore, in a nutshell, you've already been, and that's actually the requirement we got from Mr. Yo, and we want to really lead the way in terms of different measurements and indicators, and hopefully we can have more. Reason why we need to have even more verification scenarios to see the possibility of further application of that in the future. Thank you. LDPC for coding part. Thank you. Very nice presentation indeed. And now, without further ado, I would like to give the floor to the next speaker, Professor Yang Gang from University of Electronic and Science Technology of China. Thank you, Mr. Tao, for your kind introduction. And I would like to present everything in English.
Dear guests, I'm Gang Yang from University of Electronic Science and Technology of China. It is my great honor to be here today. I thank the conference committee to give me this chance to share our latest work on ambient Internet of Things. As we know, IMT 2030 has proposed 6 main usage scenarios for 6G, and massive communications is one important scenario which features the requirements of batch-free operation, no power consumption, and high-density connections. As for such requirements, ambient Internet of Things is a critical area of communications. Traditionally, low-power IoT technologies include MBIoT, RFID, etc. However, each technology has its main limitations. For instance, MBIoT suffers from limited data transmission and high power consumption. LoRa operates in the unlicensed band and has security and cost issues. RFID suffers from short distance coverage and lacks a unified standard. Recently, cellular ambient Internet of Things has emerged. It can achieve global coverage by utilizing cellular resources, realize device networking through cellular standards, can support communications over hundreds of meters, and enhance the security from the licensed cellular spectrum. As a result, cellular AIoT is promising to integrate hundreds of billions of low-cost IoT devices. To traditional active radios, the passive backscatter communications in simple AIoT device does not need any active RF chain components, thus features zero RF transmission power and micro consumption. The backscatter communication can reduce the device cost and power by 100 to 1000 times. This slide shows the standardization trends for 5G advanced AIoT. From February 2020, PP starts a standardization study for AIoT, and the first AIoT standard in 3GPP release 19 will in the fourth quarter of this year. So AIoT is a hot topic for 5G advanced and 6G research. From the technical perspective, AIoT faces three main challenges, including the multi-type, the limited connection capability, and the difficulty to integrate sensing capability. As such, we propose three comprehensive solutions for AIoT. Firstly, we propose 6G AIoT backscatter communication technology, which shares the cellular off-beam signals as the AIoT signal. Secondly, we propose 5G advanced, which adopts the dedicated singleton excitation signal at the cellular band. Thirdly, we propose the integrated sensing and back solutions. These solutions and the sensing capability for AIoT. For the first part on 6G AIoT, we propose a cellular backscatter communication design, which shares the cellular off-beam signals for AIoT. As shown in the left figure, the backscatter device transmits information to the dedicated by modulating the received cellular signal. The received signal at the IoT receiver is the superposition of the useful backscatter signal from the AIoT device and the strong direct link interference signal from the base station. This design objective is to recover the weak backscatter signal after double fading, but it suffers from strong interference from the base station. Therefore, as the main contributions, by exploiting the cyclic prefix induced repetition characteristic of the interference signal, we jointly design the backscatter waveform and the optimal detector to achieve interference cancellation and thus reliable backscatter. Furthermore, we propose a cellular symbiotic backscatter communication architecture. As shown in the left figure, the backscatter device modulates information over its received cellular off-beam signal. The cellular UE detects both the cellular signals and the backscatter signals. Thus, it is referred to as a cooperative receiver. So in other words, the backscatter transmission shares the cellular signal, the cellular base station and the cellular UE, and forms spectral energy efficient as well as cost efficient 6G IoT. As shown in the right figure, so by utilizing the designed optimal detector with two-step maximum likelihood detection, reliable backscatter transmission is achieved, and the additional multipass of the backscatter link can enhance the cellular communications. So the operator converts the inter-system interference into useful signals and achieves mutualistic symbiosis between the cellular communication and the IoT communications. Subsequently, we have proposed downlink tag communication method, which is compatible with the 4G LTE and 5G NR standard and does not affect the cellular communication. At the tag side, we have designed the envelope detection circuit for tag synchronization and detection, and single sideband QPSK backscatter modulation to improve the transmission spectrum efficiency. Also, at the cellular UE, we have proposed the synchronization and detection algorithms for uplink backscatter communication. The corresponding work will be presented in IEEE InfoComm this year. Based on this theoretical research, we have developed the tag and system prototypes to achieve simultaneous uplink and downlink communications. So under the short distance AIoT scenario, the base station transmits LT or NR optimum signal of 15 dBm. The tag is 3 meters away from the base station and 12 meters away from the cellular UE. Experiment results show that using a 500 megahertz LT signal, this prototype can achieve 1.1 mega transmission at the BER of 410,000. So comparing to the state-of-the-art, our design can decrease the BER by 6.7 times. This slide shows more measured performance of our design prototype. Specifically for the AIoT scenario at 900 band, if we take the deployment scenario for the indoor scenario, this system can achieve tens of kilobps backscatter transmission at 20 meters for passive tag and 30 meters for semi-passive tag. If we take the adjacent band deployment scheme for the outdoor scenario, this system can achieve hundreds of kilobps backscatter transmission at 200 meters for the semi-passive tag. So this performance is practical for distance AIoT applications. The second part is the 5G advanced AIoT with single-time backscatter communications. The backscatter detection under strong adjacent band interference from uplink cellular terminals is extremely challenging. Thus, we exploit the deep neural network to accurately reconstruct the adjacent band interference induced by the nonlinear. So simulation results show that the DNN-based adjacent band interference reconstruction and cancellation method can achieve 5 dB BR gain over traditional interference rejection. Unlike traditional IoT devices, the no-cost AIoT backscatter device very hardware constrained, and the backscatter communication performance is strictly limited by the hardware imperfections, such as the sampling frequency offset SFO, the and the device timing offset. So especially the SFO may be up to 10%. As such, we have designed the frame structure, the parameter as algorithms, and the singular detection methods. So simulation results verify that the reliable backscatter transmission can be achieved. In this slide, the bistatic backscatter communication system with multiple devices is shown in the upper figure. The traditional Aloha method has a limited multi-device communication capability due to its collision avoidance mechanism. In contrast, we exploit the multi-device collision to enhance the communication capability. Specifically, we leverage the state flipping property of the device waveform, such as the Manchester waveform, and advanced single processing technologies to achieve parallel decoding of the of multiple synchronous signals, multiple devices. So such a parallel backscatter transmission technique can achieve integer fold increase in throughput for 5G IoT. So as shown in this figure, we have also developed a prototype for the parallel backscatter communication. So when is 5 meters and the device to receiver distance is 10 meters. So for the data rate of 40 kilobps, so the BR for detecting devices signal is 3% without any channel coding. Furthermore, the massive access capability is also very critical for AIoT applications. In RFID systems, the slotted Aloha is widely used, which follows a 4-step access process: the query, the tag response, acknowledgement, and the data transmission. Is inefficient due to the device collisions and single device transmission, so within each slot. So hence, we propose massive access methods which enable parallel access of multiple tags within a single slot, and can boost the access efficiency by an order of magnitude. The method is the T-fold Aloha based massive random access. So each tag randomly to transmit its data with channel coding. The base station performs joint blind channel estimation and iterative data detection by using expectation maximization algorithms. The successful SIC and log likelihood ratio extraction helps to recover the data overlapping tags. Compared to slotted Aloha, the designed T-fold Aloha can improve this capability by 230%. The second method is the low collision probability pilot LCPP based massive random access. We construct a multi-level orthogonal pilot codebook to ensure minimal pilot collisions. Each passive device performs convolutional codes and BPSK modulation. So the base station identify active tag, exploits pilot orthogonality to estimate channels, and use SIC to detect tag data. Compared to traditional Aloha, so this method can improve the access capability by over 300%. The third part is the integrated sensing and backscatter communication, ISBC. Firstly, for 6G AIoT, we consider an OFDM signal excited as shown in the upper figure. We divide the received signal into multiple links and apply music type algorithms to estimate the angle and the delay parameters of all links. Then we select the backscatter link and geometrically locate the AIoT device. The signal parameters can further assist the communications. So simulation results show that besides the reliable backscatter communication, the proposed method can RMSE at a centimeter level. For 5G advanced AIoT, we propose an integrated sensing and backscatter communication architecture for NOS environment. So first, the excitation transmits a singleton signal to estimate the position information of environmental walls or obstacles. Then, based on this estimated environmental information, the position of the backscatter device is estimated. So simulation results show that the achieved locating sensing RMSE is significantly method. Also, we have started the long-distance integrated sensing and backscatter communication based on chirp spread. So the tag uses BPSK modulation, and a multi-antenna receiver is employed for AOA and TOA estimation and backscatter signal detection. This type is shown in the left figure. Experimental results show that when the base station transmits 500 kilohertz CSA signal at a power of 20 dBm, so the tag to receiver distance is 60 meters, and the relative error of tag location is less than a centimeter, achieving accurate sensing. Finally, we also have developed a prototype system for backscatter communications within Wi-Fi 7 OFDM signal excitation. So the backscatter signal is detected by computing the correlation for the signals in the specified resource units. Experimental results show that this prototype can realize 10 backscatter communications at AP to tag distance of 5 meters. Based on this aforementioned research results in ambient IoT, so I have won some awards, including the IEEE Common Award, which is the Best Paper Award for IEEE Transactions and Communications, and the first prize of Technology Cooperation Achievement Transformation, and 2 prizes for national science. This is our representative papers, including some highly cited papers. Okay, that's it. This is the summary of our work, including this theoretical research and 3 prototype systems. So that's the end of my presentation. Thank you for your attention.
NB-IoT 是其实非常受
So NB-IoT is a hot topic. It has a very good progress in CGPP. Congratulations on winning the RISE award. It's not easy. Congratulations, because it's really the most classic to win this RISE award. In the next step of the 3GPP, and you talk so much about AIoT and new designs of AIoT. What's the next plan in 3GPP? So thank you very much for your question. We have a next stage plan that is a ape system along IoT base station, and therefore it has extra costs of deployment. Sorry. So we proposed this system, which is a new structure, and we leverage this cellular base station and terminal to realize the IoT. So means we don't need to build up a special base station for AIoT. So this system can realize this information level co-share, and it can make sure that the information and the signal is shared between AIoT and the cellular. So do you need any contribution to do in the X6G standard? I think so, because for it to work, the testing sensitivity is somehow limited. Next question. I need to have a more talk with you and conversation with you offline after the meeting is over. So do you have collaboration with the China Mobile? Or if not, I want to invite you to work with China Mobile. We are still discussing. Yes, China Mobile is interested in this thing. That's good news. That's good. We have been doing it. Thank you very much, Mr. Yi. Just element. Thank you very much for. I want. So next, let's welcome the next speaker, Professor Gao Zheng from Peking. Hello, everybody. Good afternoon, ladies and gentlemen. I am Gao Zheng from Peking Institute of Technology. My topic is about the next the knowledge and data dual-driven channels estimation and feedback for ultra-massive MIMO system. So we have dual-driven channel estimation and feedback. So firstly, let's look at the background. And firstly, many reporters have said as have background that is immersive technology. Communication means we have a higher speed. We will have exponential growth eventually. And it means that when the speed gets higher and the frequency gets higher, so what are the physical support, like the voice or video chat, and actually if you look at this MIMO technology, the array will be higher for the antenna, and antenna array gets bigger, and it means it will be bigger in. We are talking about higher bandwidths, and so in this way we can shrink the size of the antenna. So we have a semi-wavelength of the possibility of better lower footprint, and therefore so ultra massive array plus ultra large bandwidth will work wonders, and they may even lead to challenges in real settings. So let's take a look at the several challenges here. And firstly, I admit that this larger array and larger bandwidth can really improve the speed of transmission.
It's basically about the coding in the first place. As you all know, I specialize in estimation for channels, and it's basically about MIMO to ultra-large MIMO, and we try to constantly improve the test methodology, and there are several challenges here. The first of all is ADC. It's very important because it can really connect this very physical and virtual world and try to do the digital processing of the signal in a discrete manner. And in this way, we see the rising of the cost, and maybe we have the low precision ADC, and also the very IQ imbalance. It can really further exacerbate the distortion of the receiving signal. And secondly, for the changes of the transmission nature or property, when the array is not that huge, it's actually a plane wave. However, it should be spherical one. And when the distance is very long, we can assume that to be the plane one. Strictly speaking, we all want to have the very relativity theory within the framework of the classic Newton laws of force. We can do such assumptions. And all the way from far field to near field, I feel like a lot of challenges simply pop up. And also, with traditional wideband large-scale array systems, we're going to see this very shifting or deviation of this very beam. And based on ADC, like low-precision ADC, we rolled out the very data-driven DQ network here. And based on this hybrid and far field, and for the deviation of the beam, for example, with its large scale, we propose this very compression sensation solution, and also we do design and improvement of the algorithm and connections. And when the users got they're going to give the feedback to the base stations, and that's the reason we have this very feedback mechanism This is actually the overall procedure for reference. First of all, we have this various, for example, from the end users or terminals to receive the signal. For you working in the area of OFDM, including those in our laboratory, sometimes they do not really consider the physical layer transfer. We know for ADC, for the data or collection, it sometimes can be overly done. And when we try to ORDMs, modularization or demodulating, we have the very over collection, and then we do and then we're going to have the very smooth signal via dequantization. And right after that, we're going to design this very algorithm to reconstruct the very with this very feedback mechanism. We're going to give that as a feedback to our base stations. And now you can see the details here. And as for the specific model here, that's basically it's hybrid MIMO. And we assume our users as single antenna or maybe a beam array, if you like. Of course, we have the IQ inconsistency thing and the low precision thing going on, and that's actually the entire bandwidth is going to go up as well, and that's actually the transmission model. And in the entire process of transmission, we have this very the guide wave being emitted, and when the UE, they're going to do the reconstruction after receiving that and then give the feedback to base stations. Going to do pre-coding, and of course in the entire process we're going to do modeling. For example, for these all those hybrid beamforming, we're going to receive all those signal, and we got those factors being considered here. That is for the consistency of I and Q, and also we do quantization as. And for Q, that's actually the bit number of quantization. Of course, sometimes we might do oversampling, and with that, we have the very W here in the equation. And besides the transmission model, we also have this very channel model. And maybe you can take a look at this very far field model. We can do modeling, of course. When the distances are larger than the Rayleigh distance, you can see the channel vector on the kth subcarrier can be regarded as a function solely associated with the angle of departure of all scatterers, but it has both things to do with this very angles as well as distances, and that's the reason why we have to carefully define that. And there's another buffer that is actually the beam squint effects. This has already been mentioned and included in several papers published, and we feel like in radar signal processing, it's already been mentioned in 1950s or 60s, called the beam squint effects. With the development of telecommunication, the MIMO's array, if it's big, I would say it's being done in recent couple of years. For radar, I would say for their improvement, it's already been achieved like half a century ago. And you can see we have this very all kinds of like near field and far field scenarios, as well as the very effects here. What are the changes to the channel? Far field scenarios, we can really have this very changing of angles domain. And we got a textbook in this area, roughly meaning that the bandwidth is limited, and for different angles within the specific bandwidth, it has the same, I would say, incident angle. And if we just change the very angles, then sometimes I would say the far field beam squint effects will take place. But anyway, the lambda is here, and when it's just too huge, the far left and far right, I would say load, it's not strictly speaking the half wavelength, and that's the reason why we really have the very deviation thing or effect taking place. And now you can see that the deviation of the load the sparsity might also be sabotaged, and it's not that sparse anymore, and that can represent a huge challenge for us. Of course, with this sparse MIMO channel methodology, it's not gonna just come in handy. That's the reason why we have done 3 things. The first one is about doing dequantization. After receiving the signal, after the ADC sampling, it has several, I would say, ways or pathways of the signals, and therefore we have the very neural network here. For this network, maybe we do not really have to dive into that, but as for the specific signal here, the blue, that's the signal without IQ inconsistency because it's really smooth. We see inconsistency of IQ there. And as for the red one, it's actually about oversampling being processed with quantization. And as for the discrete blue one, if without quantization, it's relatively smooth. And for us, after our network-based processing, like the red key curves, after quantization, I feel like the blue one will simply be the original one. However, for the red sticky things or patterns, I would say most of them are actually in line with the various signals represented by the blue curve. These network processing, the IQ inconsistency, as well as the noise derived from quantization, I would say we try to remove all of them as much as possible. And secondly, after dequantization, we can do the channel estimation, and there are several challenges. The first one is bandwidth is really high. There is still the beam squid effect, and I would say the traditional DFT dictionary is not gonna be useful. And for far field scenario, we're going to see the beam squid effect. And for different waves, and in terms of their vertical angle domain, they are not consistent. And then for DFD switch or change, it's gonna just losing its efficacy. And now we have to resolve all of them one by one. The first thing is basically about the very issue of the beam or beam squint effects when the bandwidth is very large. The load at the center is half bandwidth. However, for those at the far right and left, it's not necessarily that case anymore, and we cannot really make this very consistency assumption. Then how can we make it up really by ourselves? And different waves, they have different, I would say, beam squint effects. This is because we have this very same dictionary being used here. However, if we make it up in the first place, we still be converted into the conventional issue. That is to have this very pre-designed or pre-formulated dictionary. We can still just turn that into a conventional issue for our analysis. However, even if the array is the same in the first place, for this part it's no longer the same, and we feel like it adds to the very problem of the complexity of computing. And then for near field, I would say it's gonna be more complicated. Sometimes we'll really have to consider different dictionary for different loads or waves. And I would say it's really hard for us to really dive into the real-time processing part. Then how can we really resolve that? For base stations in a specific scenario deployment, it has its own, I would say, scattering environment. If we can really drive the network to do the self-adjusted learning to really extract the features, then I would say sometimes it's not really necessary in the entire of the scenario. That is for the direction, the dictionary can't really be self-adaptive This way, we can really lower down the workload for us while at the same time to improve the performance as a whole. And then for algorithm part, in this scenario, of course, we can resort to the very compression algorithm. That is for dictionary, our dimension is higher, then the complexity is higher accordingly. And with that, we really have to expand that at in-depth level, and we're going to do adaptive learning. And the big benefit here is that with limited iterations, our methodology can do the very fast convergence and to really have better performance. For those dB improvements, if we do that to the extreme, and we'll have to really in this way consider the marginal. Of course, we have the data-driven CSI feedback. And in the first place, the channel, we do not really have the far or near field or the very deviation effect at play here. If we still resort to this far field resolution, I would say things are not that good, and that's the reason why we use a more improve its performance later. And this is actually the very strategies for us to do the design, and eventually you can also take a look at our own work. That is for dequantization network. There are several things for your reference. Even if for those without dequantization, still the signals or the NMSE can really be good. That is the denoising effect there.
So with this 1-bit or 2-bit technology, we'll make sure that we can improve the stability. So we have the higher oversampling factor W as the branches increases in number. It means to some extent it's very much like the hyper resolution, and that means we have more information to improve it. And now let's talk about this channel estimation, several innovation. First is this stable channel, and also channel estimation. Actually, the processing speed will be faster. And then we have this feedback. And so actually, we have redesigned this internet network, and under which circumstances we can really salvage, we can really capture the near and far field of these channels. And so last, we have a conclusion. And in this 6G communication channels with ultra-large bandwidth and proposed a novel knowledge and data CE and CSI feedback approach, wideband MIMO systems considering hardware imperfections. And so we try to rebuild the CSI. And on my report. Thank you very much. Thank you very much. Do we have any question from the audience? Maybe me. Sorry, he is not using a microphone, cannot hear anything. So you talk about the feedback. The feedback. CSI feedback, yes. So we use the same spending, but we improve the accuracy. So you mean more antenna in the base station, and 206 antennas. Over. Okay, Mr. Let me just continue the question. So we have been using AI. And CGPP has been leveraging the advantages of AI to do this CSI feedback. And so, have you compared your work to that? So we do not compare yet, and because our dimension is so big. Secondly, we did something similar. That CGPP responses to so CGP is not so comprehensive in CSI feedback, and yeah, so we can do it in the future. Yes, they're very excellent. Next, let's welcome Ma Shuai, associate researcher from Pengcheng Laboratory. Yeah, you have saved 2 minutes for me. Thank you very much. It's a green one. It's a return. Okay, everybody, my dear friends, good afternoon. I am Ma Shuai from Pengcheng Laboratory. My topic today is the theory and key technologies of reliable semantic communication for 6G. 6G has a special, that is AI combined into communication, but AI limits it has a black box feature, and it has full visibility and reliability. So we need to study reliable semantic communication, that is AI being used in the encoding and decoding of semantics in communication. So we have this as a semantic channel and modeling, as well as bottleneck theory, and the fourth one is the multi-access for semantic feature division. I will focus on the inspiration, basic string of thoughts and main contributions. First is this volume or capacity. So 6G different. The semantic transmission is just about extraction and encode it, then transmit only the features, not the out and out bits. So it has some issues. So semantic computation means the bit can be losing some of its touches as long as the semantic meaning is transmitted. So that's the difference between the semantic communication and communications or traditional communications. So we thought that semantic communication can tolerate partial losses, but the meaning should be conveyed in an accurate fashion. So we try to study the capacity. We are thinking about, that is, we try to think about the multi-bit with the same semantic meaning. So different bits correspond to the same meaning or semantics. So an acceptable level of mistakes in mistakes, and so as long as we have satisfied this R, so alpha, this value, alpha is somewhere between 0 to 1. This process of proving will be just omitted. So it makes sure that it can be projected into this one. So alpha is 0 to 1, and then meaning it has many signals, so the same signal audio, and it doesn't impact the transmission of semantic channels. So it has a similar logic of proving, and it's really the proof of achievability. We also we also analyze its error probability. We also use the same method of analysis, and also we also prove its the proof of converse. And we have one difficult or challenge, that is we cannot use we cannot go through the whole thing. So that's why we deduct this non-equivalent non-equation. The second is I want to talk about the second one. So semantic transmission fidelity, and we extract, and then we have this quantifiable transmission. When you do, we have end-to-end training, and when it comes to the semantic messaging, and we do not consider connection between the semantic layer and the physical layer. So SSR and quantification bit will impact the results. of transmission. And of course, because the encoder has a smart learning process, its explainability is really terrible. You cannot have good deduction of outstanding. We try to do something. We have a very big ocean of these modeling pools, and we have a CNR, and VIT. A similar pattern, that is, the transmission quality will increase then plateau as the SNR gets higher. So yeah, based on this finding, we did a modeling. So we can turn that into an ABG. We have a fitting. So many students and teachers hope that we can have a theoretical induction. We found this pattern, that is, this end-to-end transmission will be obviously this is whole equation and quantifiable equation, and so this is the one on the left is the upper level, and secondly, when you have fixed coefficient can be well fitted, and this is the findings that we have. As SNR gets higher, we found that the upper limit is relative to the bit number of the quantification. For instance, we have CNR VAT, and it's the same logic, and the quality of transmission has this pattern, and so theoretical modeling, we can allocate resources and even control the quality. We have one simple test, which is the power control. And for this random channel, traditionally speaking, we have to use this generalization of macro, but we have end-to-end empirical modeling. The red line is the ABG best result, while the blue one is the traditional. That is of the higher chance of cessation in the middle. That is how we achieve the performance gains. And one step further, we study another theory, that is robust information bottleneck theory. And the whole thing will compress the source information volume. And to improve the reliability, we need to look at these motivations like the inference accuracy, compression, robust trade-offs. We need to make wireless signal can be very robust. We want to find the trade-off point between the accuracy, compression, and robustness. So the Y is the semantic language. X is the source. Z is the feature. Z cut is the received feature. So Y cut is inferred results. The hope is that we can have the accuracy to be maximum as possible, and also the compression. So that is X and Z cat compressive compression must have be lower than D, and also Z and Z cat must be higher than R, and that also higher robustness and stability in transmission. That is so we know that semantic encoding is about reducing redundancy, but we want to maintain some of the redundancies. The pale blue is redundancy in the coding. Blue is a coded redundancy, and red is a task relevant information, and we want to reduce the red. We do not totally eliminate this red with the green task relevant information about the robustness of transmission. This is the task we have been doing, and this is a feature extraction. Then we have the quantification. Then we have a digital transmission, and based on the theory, For instance, the blue one. This method is interesting, and the the error probability will be reduced. And we are talking about a single user. Now we also want to talk about the multi-user scenario. That is, as the user number gets higher, we actually the traditional access methods cannot satisfy the needs. That's why introduce which is semantic domain. And actually, we designed this SFDMA scheme for multi-user semantic network. That is, the encoded semantic features can be simultaneously transmitted, and they are very much cross-linked. And that is, we encode the different users. Then we have this separate feature subspaces, and X1 to X1, they are overlapping. They do not. They also have some sort of interferences. This is networks SFDMA. We also design a way of resolution. That is, for this broadcasting method, the base station will encode simultaneously the information of multiple users. And when it comes to transmission, we transmit simultaneously because they have X and Y and Z. They are vertical to each other, so they do not mess with each other, overlap with each other. And the future studies and tests show that the user one can only decode its own. If they try to use, if they cannot decipher or decode other information or by other users. So this is our test. So for two users, U1 and U2, this is user 1's features, and this is user 2's domain, and they are separate, interfere with each other. And for three users, the same story. They are very much separate from each other. We also did a comparative study. That is, SFDMA will make sure it gets higher, meaning no interference between.
By the same token, we've already talked about inference, and now we also see the very two-dimensional or three-dimensional, that is two users and three users. And also we do the data restructuring. For example, for the transmission of the pictures, for each one of the user, it can really effectively transmit their own information. If they're going to really shift from user 1 or to 2, then there's no spillover effect information, and in this way we can protect the very information. And also we have done several, I would say, outdoor experiments there. That is, use the short length wave. Very transmitters and two receivers, and we can see that there's no spillover effect there of information. To sum up, we talk about, for example, ABG, as well as the theory of robust information, and also SFDMA scheme to really the very semantic communication, but there are still very open questions to be resolved. For example, the semantic entropy, and also general semantic channel coding theorem. It's something up in the air. The publications and also the list of references. That's it from my speech. Thank you for your attention. Any questions at the moment? I have a puzzle hanging in my mind. For semantic communication, its performance as well as efficacy are heavily dependent on your goals and purpose. Is that the case? For me personally, I feel like for objective and subjective measurement, and that turns out to be helpful in my view. It's not a purely universally applicable solution or objective. For receiver side, what kind of tasks are going to accomplish? You need to choose your selection of the outcomes, and in this condition, I would say semantic communication will be effective and useful. Then what about the objective limits there for semantic communication? At the moment, we're still task-oriented. that is to have a very clear task. That is the finite set, right? And as for the outcome, it's a finite set. And for transmission part, we all need to do is just to fit enough information and to do the very receiving or and I feel like in this circumstance or scenario, it's really hard for me to really think about its fundamental limit that can be universally applicable, because there's a precondition of finite. That's the issue. We use computing and transmission to do the trade-off. In the first place, for conventional way, we can only do transmission of the texts, and also for 3 KB, we can use. Then what about alpha, beta, gamma here? Is it a row found? For, I would say, encoding part, it's actually a neural network for learning, and it's about to infer their information, but from the perspective of engineering, we do the modeling by ourselves. Yes. And of course, we can do the explanation from the perspective of theory. Why is the trend there? And also last year, we talked about semantic. Its meaning in Chinese. Is it the first E or the second E in Chinese? Currently, it's about the second E in Chinese, and then it's an objective measure. For the former, it's subjective, right? And if you want to draw a clear line, that's actually the nuance or subtle difference. You need to, in this way, know whether it's subjective or objective. Right, thank you for your very insightful opinions and feedback. It's really interesting. And obviously, we know that Zhangfei has spare work. And with that, I would like to call upon Ding Shengli, Senior Engineer of Vivo Communication Research Institute. Please come up to the stage and address the audience. Ladies and gentlemen, and dear experts and students, greetings to you all. First of all, I would like to thank the organizer to invite me to be here. I'm Ding Shengli, coming from Vivo Communication Research Institute. I used to be T2030. I would say for you should be familiar with the fact that for Vivo, we really focus on the very work we in work groups. For China Mobile Research Institution, they might focus a little bit more on the very synergistic, I would say, sensing. For us, we work on dual sensing. And in the white paper released yesterday, for this very verification research of dual GB, a lot of work, and it really helped us to understand the work results we have. And of course, our counterparts have provided a lot of good input for us. If you're interested in that, write your feedback to us based on the white paper. And this is info. From the left-hand picture, you can see that for the ISAC, this is actually a very important scenario for 6G. And on the right-hand side, on your right-hand side, it's basically about the standardization of ISAC. And for Rail 19, we try to do the modeling for the use cases as well as SNR, and we have different cases. And for Rail 20, or R20 if you like, we have done, for example, signal design, measurement, quantity, definition, and report, and also use cases and further researches in this regard. And for two base stations or dual BS, I would say modes or CNC modes altogether, we have these very four of them. It's already been highlighted in green here. For I would say important. And in terms of system architecture, one important piece is about the definition of the very sensing and measurement. We have different, I would say, definitions level and also measurement quantities like delay Doppler angle or the first level of received signal or channel information, or the level 3, the top level sensing results such as targeted trajectory and respiratory rate. And for all those information introduction, it's about 6G standardization related content. For 6G standardization as well as standardization of ISAC, I feel like it should have its own foundation. For sensing, its sensing measurement, it needs to have reliable outcomes. I feel like that's the precondition for everything we do. For sensing, it's different from monostatic sensing. Of course, it has its own shining points. First of all, it's in no need of full duplex capability, and therefore we do not really have this very self-experience. And also, it requires only minimal or negligible modifications to legacy devices and protocol. And in ideal condition, we do not need extra hardware. And also for the reuse legacy framework, we can minimize all of them. And also, as you've just discussed, whether we have to extend CP to cover this very latency, there's so no such need anymore. And one more thing, for bistatic sensing, it has its own games in specific circumstances. If the target is very close to UE, and then it does not really have to do those two-way latency of transmission. I would say for loss of transmission, it can be minimized, and also it can really have better gains in terms of signal transmission, and that's its pros. Then what is the challenge for it, really? That is the synchronization issue. For bistatic sensing, I would say for a long period of time, it's actually a very important issue we need to laser focus on. And for all the synchronization issue, we have summarized several things. Timing offset, timing drift, and also carrier frequency offset. And also, we also have phase-related issues being identified, and maybe we can include that also in timing drift, that is TD. And for timing offset, I would say it's different from the definition in literature. It basically refers to the CPI value, and that's actually the original value as we've been emphasizing. And then for TD, it describes the variation part of time offset, and basically it's induced by the clock periodicities mismatch between the receiver and transmitter. And finally, for CFO, it's basically for the difference in local frequencies between the receiver and transmitter. And what is the result really, or efficacy? You can see the comparison for the left-hand picture. Altogether, we got three of them. That is the monostatic sensing, that is with perfect synchronization. And you can see for delay and delay Doppler spectrum and delay Doppler spectrum. So we have already got the very highlighted areas that should be easily detected or sensed. However, for bistatic sensing, due to synchronization issue, for example, the OFDM symbol index is not aligned anymore, and it's really messy. And you can see in this way, the Doppler spectrum can also witness the same situation. And in the entire, I would say, spectrum, there are a lot of, I would say, messy situations going on. And this is because of the diffusion And for those three targets, they could not really be detected or sensed, as they have already been really overshadowed or interfered with other diffuse targets. And in terms of academia, we have, for example, CSDR methodology and also reference caliber methodology. They can do the offsetting, that is to specifically choose a reference in a domain and then take that as a benchmark. And then for the same synchronization issue, we eliminate all of them. Of course, they got their own workflows. And then for us, for monostatic sensing, we use traditional radar technology, and for bistatic sensing, could we also rely on the traditional and this is actually the biggest issue or barrier. And you can see we have already highlighted the asynchronization issue. If we can really resolve that, then we can continue to use the radar technology. And in this way, the static sensing technology, it can be easily implemented on the ground. And then for all those, for example, the TL and TD CFO issues, we analyze all of them. And for this delay issue, there are two things to it. The first one is about the very phase drift as well as delay spectrum shift. I would say it's an overall shift on the spectrum, for which it's actually caused by the TO or TD, and therefore the focus for us is just to really resolve this very drift. And there are two factors here. The first one, as you see, as indicated by this picture, this is actually about the part. It's actually about the phase drift, as we've highlighted here in this formulation.
By looking at the equation, we can see as a linear connection, and it's easy to make a phase compensation, and contralateral deletion is just not a good way, and competition like this one and needs no references, and this is our solutions to suppress TD. And so firstly, we have this one. We have oversampling IDFT, which is adopted to reduce the sampling interval in delay domain so as to handle fractional shifts of delay spectrum. And in the past, we need a lot of very big bandwidth, but now we don't need a bandwidth. Even we can still have very precise alignment, but after the alignment, and after these semesters, we have this phase of compensation, meaning we do not need references and we can have direct compensation. And this is the end result. We make sure that we can identify this spectrum, and we try to find the shift value. So then the shift alignment. That's the first step. Secondly, we have this compensation, and then we do this slow time DFT. Eventually, we have this time delay Doppler spectrum. It's very close to the monostatic. Then we try to remove these miscarriers, and eventually we have these results. We can see that compared with it's very similar to the monostatic. So the result is easy because we can use traditional radar methods, including this detection, parameter estimation, coordinate transformation, all these things methods. And our studies have one purpose, that is for the 2D FT, we have a good addition, and that's what our technology means. and the value of a technology. And also, we have this prototype testing and testing as well to USRD. And in it is Vivo's self-developed 5G base station, 5G UE station. We use DMRS, which was reused. Extra time frequency resources was configured, and we have 1 sending, 8 receiving, so 8 channels for receiving end. And we want to measure our performances, and we have the same antenna deployment. It's a very perfect synchronization. On the right is our testing result. These are the perfect synchronization. On the right, we have the eventual result, and we have two-phase compensation methods. You can see, it's very similar to the perfect synchronization. Eventually, we got the centimeter level precision, and the diameter is 3 centimeters. Has good efficacy. And also, in different settings, we have shown our demonstration. One is in the IMT 2030 ISAC organized by CAICT. We also won the best demo award at the academic symposium, and also in Shenzhen, we got the best demo award in that academic symposium, which is at ISIC, and in last year, China Mobile's Global Partner Conference and in China Telecoms Conference, we exhibited our solution. It's a game, it's a toy car, a toy vehicle, but we have very good real-time follow. We just say that we do not need any references, meaning that's one feature. We don't need this. We don't need to have these loss mirrors. And in the future, the key work for us is to do the last step. That is, how do we make sure our algorithm can work perfectly? And we are very close to the completion of work. This is the end of the report. Thank you very much. Any question from audience? So I'll be thinking. Our team did a lot of bistatic, and so UE plus bistatic, right? Your receiving end is the downlink, right? Yes, or the other way around. For bistatic, the receiving end is uplink. That you don't need to pay any price, and you can reuse. This is what is special about the advantages. But on the other hand, in actual conditions, I rely on the UE to do the work. So what to do with the UE? Because I'm doing the sensing and testing and the localization. So it means we are using our own base stations or our units, right? But now, the UE is on the internet. I rely on the UE to do the work. I'm not so sure. I mean, how to implement it. So I want to answer questions. Firstly, we look at this. We talk about the downlink. You can also use the POS HD, and so it really solves the issue of internet as a sensor. It means UE is just as a sender and transmitter of signals. Everything else is just handed to the base station. That's the first point. So we use the reference signals from the uplink. So UE and base station work together. Instead, it says UE as transmitter and base station as a receiving end. Yes, I need to think about this things in the internet. How is the UE connected to us? Because yes, it's really a good question. Another thing is that so can we do something about UE? Results show that we don't need to use UE if it moves, and it will have multiple Doppler. So you call it UE, but it's not really UE. It's the deployed UE similar. Yes, it's a customized UE. For instance, mounted on the wall or just mounted around the roadside. And it's not like a base station, it's more like a UE. Devices like a customized UE. This is a better way to describe it. We also use 400 mega the eventual precision, because you use centimeter precision. Theoretically, it should be 0.76 or 0.67775 for the precision, but we use hyper resolution. So we use some raised super resolution by static sensing. It means the receiving and sending part of the signal are just two different independent devices. It's called bistatic sensing. Independent devices, no connection whatsoever. So I feel that I want to use this approach. Not rely on everybody. It's just that on the internet there is this specific deployment of special purpose UE, and so for this localization and the positioning, it has requirement. And for other conditions like respiratory monitoring or heart monitoring, we can use general UE for cell phone. By my side when I sleep at night, and the cell phone can be used as the monitor of my respiratory. Very interesting. Thank you. So we have one speaker who is associate professor, a doctoral supervisor from Shanghai Jiao Tong University. So they are leaders and experts and my dear students, and good afternoon. I'm very happy to tell you something in this global 6G conference. And the title of my speech is 6G meets broadcast, building a greener, more sustainable multimedia network. How do I turn the pages? The big button. This is my background, 3 things in my background, and 3 things in outline. Firstly, I'll talk about the background. And so, as we know, the ground broadcast in USA and EU, they are more used, and 10% of the population are still using the very traditional broadcast to watch the streaming. But recently, as time goes by, the TV less and less used, and you can see TV sellers or sales have been on the decline. That the traditional broadcasters have and the crisis, and we can see that cell phone terminals or mobile terminals have become the mainstay of media consumption, and so whether it is now or the past future, traditional broadcasters, even 3GPP broadcasters, are making effort to develop new technologies and standards to expand the broadcast services for various mobiles like ATSC 3.0, and they have been working in India. They work with Tata Group and Indian governments together because they want to integrate these things in their cell phone. A few years ago, India policies say that must the compulsory cell phone. That is, all the cell phone entering India must have broadcasting function. And this government announcement was rejected by Qualcomm and Apple, and they were still undergoing some process of negotiation. Traditional broadcasting trying to enter, but CGPP broadcasts actually in 2004 have this MBS services. I think it was called Release 6 as the business gets stronger, and actually CGPP is in version of Release 16, and as broadcasters 5G MS bigger or EMTB plus were being introduced using. And we can see that in last year's IBC in Europe last year, the World Cup and also the Olympic Games, and in France, they have tested the 3GPP broadcast and the Xiaomi's terminals. And so France's TDF, the France broadcasts, and USA's 60 broadcast operators voiced the hope to transition to the newest 5G network. And so from this aspect, you can see that broadcast to really integrate their business into our cell phones. So we look at these satellite communicators. They have all running to this 3GPP because they want to have a wider.
For 5G, at least in China, it's successful, but not necessarily the same in EU or US. One of the reasons is for its total consumption. It's really big. For 5G, it's going to be higher than 4G for its own frequency points, and it has to adopt, I would say, MIMO technology. And I would say for base stations for 5G compared with 4G, the power consumption is going to be up by 1.5 to 3 folds. And for energy consumption or power consumption, it's an issue, and also for 6G. And you might have different opinions on that, but currently I would say it's about 50 to 100 times higher when it comes to its own traffic load, leading to much more or greater power consumption. We totally agree with each other that a more efficient and greener transmission, I would say it's going to be a very important topic for 6G, and therefore for efficient and green transmission becomes in this way extremely crucial. And then what about broadcast as well as the cellular network? Advantages for broadcast, it's very public. For the same information, live streaming sessions or streaming of video clips is going to be really efficient and green. However, the big disadvantage is that it cannot enable two, and therefore it cannot redo the transmission, and there's no, I would say, tailor-made service as well, and that's going to be the very advantage of cellular on the other hand. And however, for high traffic transmission, I would say the efficiency of transmission for cellular can be really low. Be it for 5G or 6G, first of all, the broadcast is transmitting its own video content to the mobile phones, and for broadcast, it's one-way transmission. Unlike cellular, which knows about the CSI feedback from users and then have better beams. And therefore, for broadcast, it has to constantly improve its physical layer technology. For example, for coding and modulation technique, basically, and it by or used in broadcast. However, for cellular, for MIMO technology, it's very important because it cannot be used by broadcast. It's all-phase antenna, instead. However, it can be improved, I would say. The problem is still there. That's the reason why 6G could really help it in time to make sure its service can really be continuously sound and smooth. And for one more thing, we might not really need that if the traffic utilization is not sufficient. If it's going to be successful for NTN, for EMBB success, I would say, the XR's application will have to be there. If we got such things, I would say the traffic could make operators willing to throw themselves in the building offering. And now we're working, if we also watch XR video streaming and the traffic is huge, even for 6G, you can have your own, I would say, very intensified network. I would say it's not that green. And finally, they can have the cooperation. For example, we're going to watch 3D program, the 2D or the background, or if we have a mobile game going on, it's a 3D game, I would say the background information, it can broadcast. However, for cellular, they can be handling all those tailor-made information, and eventually at terminal end or terminal users end, we can just coordinate both of them. And also we have the large areas in Beijing, and also we have 30 kilometers distance between different base stations, and also we have on-demand video and video. They are distributed like this, and also for its on-demand businesses, we basically do the modeling based on the more than 20 million times of requests on iQIYI, the platform, and after we have done the theoretical analysis, something interesting. For broadcast, if it's up and running, it can significantly improve the very video live streaming users number, while at the same time, within 1 square kilometer with over 5 users watching the same program, when the broadcast is there, then the energy consumption is far better. If the user's number is over 250 in 1 square kilometer, I would say we can have 1.5 thousand watts energy reduction for broadcast. And after theoretical analysis, the gains are there, but we want to do 2 more things to make it more practical. First of all, for the current 3GPP, and also for AG 3.0 from US, I would say they're still really left behind in terms of its technology. And we have already done our piece of work in this area. Hopefully for 5G broadcast technology can be going beyond the limit. And we have our core network work, and we want to really build the core network for broadcast to really have this higher level convergence with 6G. That's the 2 points I would like to emphasize. First of all, for 3GPP broadcast, I would say from 2004, we started to work on MBMS. At that time, we also got CDMA, and we have EMBS, and also the single frequency network as well. And after release 13 or 14, there are 2 ways. The first one is about 1 tower or single tower broadcasting, but now it's constantly evolving all the way to release 18. That is still to do different combinations for the single area, and the other route or route here, it's network, its physical layers are similar to each other, but it's independent, and in this way we can really do the wider coverage businesses. Basically, it's going to be supportive to TV, media, or video streaming scenarios. We would like to focus on 3GPP broadcast instead of conventional ones, because be it for protocol or end user ecosystem or industrial, I would say, ecosystem accessibility, I would say it's going to be easier for us to integrate everything. It is has a lot to do with the very interest of operators. And now we can also do a comparison among, for example, this one as well as DVB and those from the United States. Still, there's a huge gap. But the biggest gap is that if it's on the move, on the left-hand picture, it's a trip doing its experiments in Jeju Island in South. Actually, a loss of 7.5 dBs performance, and also with 120 kilometers. When we are running our own simulation, we found such. We have done our own analysis. Compared with ATSC 3.0 from the US, the most advanced 5G technology in China, encoding and modulation, it's a loss of 1.3 dB performance. And for customer, I would say it will be 1.2 dB. And then for frequency time, selective channel for about 3 to 8 dBs performance. And in Shenzhen, in Pengcheng Laboratory and in Wutou Mountain there, we put in place our own on the field trials, and it's actually having the HT height of 800 meters for 65 watt for each one of them in terms of power. And if we only use this existing 3GPP technology, efficiency per second per hertz 6%. However, if we increase that a little bit more, then successful reception can be a lot lower, and therefore we could not really handle the very lost performance with the time passing by. Of course, we can do a lot of things like modulation and also time frequency interleave. And I used to work in LDPC, and we have in this way very compatible 5G encoding. And in 2015 in AIMS, we really proposed that is the non-uniform modulation. And right after that, for 1 point or so, once again being recovered, and a lot of the content is already been included in the release 16 standards. And one more thing, we're glad to find that in December last year, we worked together with Qualcomm and EBU and Samsung and other major players in Spain or Madrid. We really promoted the initiation of 3GPP, and in terms of 3GPP, we were having a little bit luck, and we really want to have this very time frequency interleaver because it can really lead to the loss of 3 to 8 dBs performance. And this week it's really lucky for me because from Monday to Thursday I was in Wuhan, and that's actually the formula or equation I proposed, and with that it has already been included in the 5G standards. It can really help us to have the achievement of minimum span, and between the two towers like this, we have this very strong delay leading to periodical loss of performance. And in order to offset or withstand the test of that, in terms of the design, and which have already been acknowledged by different companies already, and also for physical layer, we have already included our optimization in prototype, and therefore in the future possible industrialization process, we can really be in a better position to be successful. And finally, as I've just mentioned, we want to push the boundaries of the physical layer of the 5G broadcast. Why 3GPP in the first place? It did not really think like this because they have different methodologies, and if it's going to change legacy, the complexity really increases. And after we have improved and boosted up the property of physical layer, and eventually we're going to lose way. That's the reason why we have been working together with our counterpart to really work on the 6G and broadcasting converged network building. And with these with these projects going on, hopefully in terms of the network controller level, and also with the fusion of these very resources and for the final user or end users application, we can integrate all of really design this 6G broadcast core network. It has gateways, while at the same time it has its own intelligent and smart processing units. For gateway, it's about management of the broadcasting businesses, and also the sessions management as well, and also the service announcement. And as for CIPE, I would say the function for that is just to trigger the management of the data related data as well as the information processing data. And for the 5G or future 6G network core network, we're going to achieve the consistency, and in this way we can have this broadcast network management capacity, that is to really have the very data in this area in our own hands to really have this better interaction between 5G and 6G. And this is a traffic offloading. We got 3 users or multiple users receiving the same piece of information at the same time, and then with the triggering, we can trigger the very gateway and to do offloading accordingly. And when it comes to loss of performance in the process, we can do our work to really make it up by using 6G. And finally, for broadcasting as well as cellular, they can really be responsible for transmitting different content eventually to have the merge eventually.
So in Shanghai Jiaotong University, we have set up one broadcasting tower, and we have done some preliminary study. That is, in when it comes to offloading, we can reduce our energy consumption, and also our some so very continuous. And when it comes to the content update, when it comes to integration of businesses, we have done some preliminary demonstrations. We will improve in the future. Based on that, this March in the 3GPP workshop, I proposed something that is which is called Building the Foundation for 6G Critical Broadcast Requirements for Next Generation Collaborative Network. We hope to make our voices in the verticals. And it is because 6G, beginning from this March, has been standardized. And I hope that in the standardization part, we can inject new values to the success of the 6G. Make our contribution. Thank you very much. So, I'm always thinking about many activities around 2000. Do you remember CMB? I do. It was related to the Beijing Olympics, but that system was decommissioned. B replaced the CMB, but DTMB is relevant to cellular or China Mobile. When I was still in Hong Kong, China, I transported the thing to DTMB and city worldwide to do the DTMB, but CMB broadcasting and combined together was a point of endeavor for many generations of people. And some people will be talking on white papers that in the future internet may be very wide range and wide covering, and but our consideration is not for the capacity, but the control signal wide coverage. The broadcasting must have some requirement in the capacity or volume. And also, I remember that many people are debating. So broadcast. So if we combine it with the cellular, do you think that multicasting is a more connected modality of services, and congratulations on these cases in 3GPP. You have made your case in 3GPP. I'm curious about one thing, that is the major pushers in this aspect. Who are your main global partner? Thank you, Ms. E. Let me ask you a question. Qualcomm and Samsung, and also EPU from European. You have collaboration across 3 regions, and we work with IBS in China, and also accompany broadcast sciences, and also Shanghai University work with Tsinghua University, but also China Mobile. And I think that they are also waiting and watching, because they want to see if there is any needs. Actually, I just report to you that India may just have this kind of needs. It's just that they are not so sure if they want to choose the 3.0 or 0.0 or the 5G broadcasting. 5G broadcasting has many substandards, and many broadcasters across rich cities want to do this 5G. And the TDF from France announced that they want to commercialize this thing in around 2028, and actually commercialization of the multiplexing is subject to a lot of changes, as you have mentioned. So, or we have considered like multicasting. Multicast, I didn't talk about multicasting. We have done some work in multicasting. Only 2 parts away. 5G multicasting, 5G NBS, that is 5G multicasting, and that is in the standards of 5G, and it's more in the community. And if there's 3 users, and the video will be multicasted to these users. If not, and so it's more like less of a physical work. It's like it's more like a natural work. So it's more natural, but it covers very small areas, right? And it just have this 55 millisecond CP. People have different frequency points. Yes, it's a separate system. So we don't really care about if 6G or not. But we are really going for a 6G. Thank you. Thank you very much. Thank you very much, all the speakers and reported in the afternoon part. And thank you very much, Mr. Zhang, Ms. Yi. All the audience and members. I'm not sure if I want to have thank everybody. And just time limit up. I want to announce today's meeting a fruitful conclusion. And I'd like to invite Mr. Zhang, Ms. Yi, and reporters, please come to the stage and take group photo together. I want to say something else. I'd like to thank young scientists for their wonderful share. So we want to thank the GTC's president, Mr. Mao. This program costs you a lot of time. The same is true for Zhang. You have read every word of the papers. So actually you have been well selected and you are really strong in your ability. Thank you very much. Let's come to the stage and take group photo. Thank you very much.
那个老师们先合照，如果后面有愿意和那个老师合照的，也可以稍等一下啊。好。好嘞。好嘞。有没有想集体合照的，可以赶紧上台和大家合一张啊！有没有各位老师？大家一起上来合一张呗，老师们，好吗？一起上去合一张去，快点，快点，快点，快点！
我们几位专家可以站前面一点点，然后让他们可以站到后面。对，我们专家都可以往前，就站前面吧，可以的。不会吧？没有，我们可以站2排好吗？我们专家站前面，然后我们后面的小伙伴可以站到我们的2排。你开心就好。我们不用。对，可以。我们的小伙子、小姑娘可以蹲在前面，好不好？对，我们前面一排都可以，还可以坐在这儿，都可以，都会，好吧？来，我们后面小姑娘来往前嘛，往前，对。OK， 在前面位置多呢，来，小伙往这边来一点。OK， 我们近一点。OK。好，谢谢大家，辛苦了。摄影老师，等一下。